It all begins not in a grand laboratory, but in the mind of a curious child. Imagine a young Albert Einstein, just 5 years old, sick in bed in Munich, Germany. His father gives him a simple magnetic compass to play with, but for this particular child, it was no mere toy. He was mesmerized. What invisible force, he wondered, was reaching out across the empty space to make that needle point so stubbornly north? This profound sense of wonder, this fascination with the unseen forces that govern our universe, was the spark that would ignite a revolution in human thought. It was the first inkling of a mind that refused to accept the world as it merely appeared, but insisted on understanding the deep, hidden rules of the game. As he grew, this curiosity only intensified. He was not a model student in the rigid German schools of his time. He was rebellious, questioning authority, and preferring his own path of learning. By the age of 16, he was already wrestling with a question that would occupy him for a decade. He performed his first great thought experiment, a tool he would use throughout his life to explore the cosmos from the comfort of his own mind. He asked himself, what would the universe look like if I could ride alongside a beam of light? Would the light wave appear frozen, a static, shimmering field suspended in space? This simple yet profound question set him on a collision course with the established physics of his day. The idea of a stationary light wave seemed impossible. It contradicted the elegant equations of James Clerk Maxwell, which had unified electricity and magnetism, and showed that light was an electromagnetic wave that must always travel at a specific, constant speed. You couldn't just catch up to it and see it standing still. This contradiction between how motion should work and how light did work was a deep puzzle. It hinted that something was fundamentally wrong with our understanding of the universe, a crack in the very foundation of classical physics laid down by the great Sir Isaac Newton 2 centuries earlier. This was the kind of problem that Einstein's mind was uniquely suited to tackle, so while his peers memorized facts and figures, Einstein was voyaging through the cosmos in his imagination. He was a visual thinker, picturing problems and their solutions. These mental journeys were not idle daydreams, they were rigorous investigations into the nature of reality. The compass had taught him that invisible forces were real and powerful. The light beam thought experiment was now telling him that our common-sense notions of space and time might be illusions. The stage was being set, not in a university or a laboratory but within the boundless universe of Albert Einstein's mind, for a complete overthrow of our understanding of space, time, and gravity. Life after graduation wasn't easy for the young physicist. After clashing with his professors at the Zurich Polytechnic, Einstein found himself unable to secure a teaching position. The academic world, it seemed, had no place for this brilliant but unconventional thinker. So, in 1902, he took a humble job as a third-class examiner at the Swiss Patent Office in Bern. It may have seemed like a detour, a step back from his grand ambitions, but this unlikely setting proved to be the perfect incubator for his revolutionary ideas. His job was to analyze patent applications, many of which were for devices designed to synchronize clocks across different locations. Day after day, he was immersed in the practical problems of measuring and coordinating time. This seemingly mundane work kept the concept of time at the forefront of his mind. While his official duties required only a fraction of his intellectual energy, he used the quiet hours at his desk to secretly chip away at the fundamental problems of physics. He had the freedom to think without the pressure of academic expectations. The patent office became his sanctuary, a place where he could wrestle with the giants of science. He saw a deep conflict between two pillars of physics. On one hand, there was Isaac Newton's world, where the laws of motion were the same for everyone, no matter how they were moving. On the other, there was James Clerk Maxwell's world, where the speed of light was a universal constant, always the same for all observers. How could both be true? If you are on a moving train and throw a ball forward, its speed relative to the ground is the speed of the train, plus the speed you threw it. Newton's laws were clear on this, but Maxwell's equations insisted that if you shone a flashlight from that same train, the light would not travel faster. It would move at the same constant speed, c, whether you were on the train or standing on the platform watching it pass. This was the great contradiction that had been born from his teenage thought experiment. One of these titans of physics, Newton or Maxwell, had to be wrong, or perhaps both were right, and our understanding of something far more fundamental was flawed. Einstein, the patent clerk, chose to trust both. He took the constancy of the speed of light as an undeniable fact of nature. He also held on to the principle that the laws of physics should be the same for everyone. If both of these were true, then something else had to give. Something we took for granted, something that felt absolute and unchanging, had to be flexible. That something, Einstein realized, was time itself. The patent office, with its obsession over synchronizing clocks, had inadvertently provided the perfect environment for him to dismantle the universal clockwork of the Newtonian universe and build something far stranger and far more beautiful in its place. The year 1905 would become known as Einstein's Annus Mirabilis, his miracle year. From his desk at the patent office, he published 4 groundbreaking papers that would forever change the course of science. One of these papers introduced the world to the theory of special relativity. To solve the riddle of the train and the light beam, Einstein used another brilliant thought experiment. Imagine a lightning bolt striking both ends of a moving train platform simultaneously. For a person standing in the middle of the platform, the light from both strikes reaches their eyes at the same moment. They would rightly conclude the strikes were simultaneous. But what about a person sitting in the exact center of the moving train? For the passenger on the train, things look very different. Because they are moving towards the light from the front strike and away from the light from the back strike, the light from the front reaches them first. To this moving observer, the lightning strike at the front of the train happened before the strike at the back. Both observers are correct in their own frame of reference. The startling conclusion is that simultaneity is relative. 2 events that happen at the same time for one person can happen at different times for another person who is in motion. This shattered the centuries-old idea of absolute time, the notion that time flows at the same rate for everyone, everywhere in the cosmos. This insight had profound consequences. If simultaneity is relative, then time itself must be relative. Einstein showed that the faster you move through space, the slower you move through time, relative to a stationary observer. This phenomenon is known as time dilation. It's not a trick of perception, it's a fundamental feature of the universe. If you were to take a trip on a spaceship traveling near the speed of light, you would age more slowly than your friends and family back on Earth. When you returned, you would be younger than them. Time, the seemingly unwavering river, could be stretched and compressed. Each of us carries our own personal clock, and its ticking rate depends on our motion. Out of the elegant mathematics of special relativity fell the most famous equation in all of science, E equals mc squared. This equation revealed a deep and startling connection between energy and mass. It states that mass is a highly concentrated form of energy, and that a small amount of mass can be converted into a tremendous amount of energy, multiplied by the speed of light squared. This simple formula explained the power source of the stars and unlocked the potential for atomic energy on Earth. The patent clerk had not only redefined time and space, but had also uncovered a fundamental secret of matter and energy, all by daring to question our most basic assumptions about reality. Special relativity was a monumental achievement, but Einstein knew his work was not yet complete. His 1905 theory described a universe with constant motion, but it didn't account for acceleration. More importantly, it had nothing to say about gravity. And this was a major problem. According to Newton, gravity was a force that acted instantaneously across the vastness of space. If the sun were to suddenly vanish, Newton's laws implied that the Earth would instantly fly off its orbit. But special relativity had established a cosmic speed limit. Nothing, not even information, could travel faster than light. Gravity couldn't be instantaneous. Newton's revered law of universal gravitation had to be wrong. The breakthrough came to Einstein in 1907, in a moment he would later call his happiest thought. He was sitting in his chair at the patent office when it struck him. If a person falls from the roof of a house, they don't feel their own weight. In that moment of free fall, they are weightless. From this simple observation, he formulated a profound idea called the equivalence principle. He imagined a man in a windowless elevator or box. If the box were resting on Earth, the man would feel the force of gravity pulling him down. But what if the box were in deep space, far from any planet, and was being accelerated upwards at a constant rate? The man would be pressed to the floor in exactly the same way. From inside the box, there is no experiment the man could perform to tell the difference between being in a gravitational field and being in a state of acceleration. Gravity and acceleration, Einstein realized, are indistinguishable. They are 2 sides of the same coin. This was the key he needed to unlock the true nature of gravity. It wasn't a mysterious force reaching out across space, as Newton had believed. Instead, it was a consequence of the very structure of the universe itself. This happiest thought set Einstein on an arduous 8-year journey to develop a new theory of gravity, a theory that would incorporate acceleration and special relativity into a single, cohesive framework. This idea had bizarre implications. If acceleration can bend the path of light, imagine a laser beam shining across that accelerating elevator. Its path would appear to curve downwards as the floor rushes up to meet it. And if acceleration is equivalent to gravity, then gravity must also bend the path of light. This was a radical and testable prediction. Gravity was not a force that pulled on objects. It was something that affected the very fabric of reality through which objects move. The journey had begun to move beyond special relativity and into a far more comprehensive and mind-bending theory, general relativity. To build his new theory of gravity, Einstein first had to reimagine the stage on which the cosmic drama unfolds. Newtonian physics described a universe with 3 dimensions of space, length, width, and height, and a separate absolute time that marched forward for everyone. But, special relativity had already shown that space and time are inextricably linked. Building on the work of his former teacher Hermann Minkowski, Einstein embraced a new concept, a 4-dimensional reality called spacetime. Think of it not as 3 dimensions of space plus time, but as a unified 4-dimensional fabric. Every event in the universe has a unique address in spacetime, a specific location in space at a specific moment in time. And in this new picture, objects don't just move through space. They follow paths, or world lines through the block of spacetime. If you are sitting still, you are still traveling through time, so your world line is a straight line pointing into the future. If you are moving, your world line is tilted. This 4-dimensional fabric was the canvas Einstein needed, but in its simple, flat form, it still didn't include gravity. The equivalence principle gave him the next crucial insight. If gravity is equivalent to acceleration, then gravity must be a manifestation of spacetime itself being distorted. He came to a stunning conclusion: mass and energy tell spacetime how to curve. Imagine a flat, stretched-out rubber sheet. This represents flat spacetime, far from any gravitational influence. Now, place a heavy bowling ball in the center. The sheet curves and warps around the ball. This is what massive objects, like the sun, do to the fabric of spacetime around them. They create a gravity well, a deep depression in the cosmic fabric. Now, if you roll a smaller marble nearby, it doesn't get pulled towards the bowling ball by a mysterious force. Instead, it follows the straightest possible path along the curved surface of the sheet, causing it to spiral inwards. This is what we perceive as gravity. Planets orbit the sun because they are following the curves in spacetime created by the sun's immense mass. This was a complete redefinition of gravity. It was no longer a force, but a feature of geometry. As the physicist John Wheeler would later elegantly summarize it, spacetime tells matter how to move. Matter tells spacetime how to curve. But describing this complex curved geometry required a new and incredibly difficult kind of mathematics, one that was far beyond Einstein's expertise. He needed help to find the right language to write down his ideas. The intuitive vision was there, but he needed the formal tools to turn that vision into a predictive, scientific theory that could be tested against the real universe. The path from the happiest thought to a complete theory was long and honestly fraught with difficulty. To describe the warping of 4-dimensional spacetime, Einstein knew he needed advanced mathematics. He turned to his old friend and brilliant mathematician, Marcel Grossmann. Einstein explained the physics he was imagining, and Grossmann identified the perfect tool for the job: tensor calculus. This was a complex branch of mathematics developed decades earlier by Bernhard Riemann, which provided the precise language needed to describe curvature in any number of dimensions. For the next several years, the two friends collaborated, struggling to translate Einstein's physical intuition into a set of coherent mathematical equations. By 1915, Einstein was in Berlin, separated from his wife and children, and working with feverish intensity. The First World War was raging across Europe, but Einstein was engaged in his own battle of intellect. He learned that one of the world's most renowned mathematicians, David Hilbert, had also become interested in the problem and was working towards a similar theory. The friendly collaboration had turned into a high-stakes race to the finish line. In November of 1915, Einstein committed to giving 4 weekly lectures at the prestigious Prussian Academy of Sciences, intending to present his final theory. But as the lectures began, he realized there were still flaws in his equations. Under immense pressure, with Hilbert closing in, Einstein worked tirelessly, correcting his mistakes week by week. He was living on the edge of his intellectual and physical limits. He later described it as one of the most stressful periods of his entire life. In the midst of this race, he decided to test his evolving equations on a real-world problem that had stumped astronomers for decades: the anomalous orbit of the planet Mercury. Astronomers had long known that Mercury's orbit wasn't quite stable. It wobbled, or precessed, in a way that Newton's theory of gravity could not fully explain. There was a tiny discrepancy that no one could account for. In the final days leading up to his last lecture, Einstein plugged the numbers for Mercury's orbit into his nearly final field equations. The calculations were agonizing. When he finished, the result was breathtaking. His theory predicted Mercury's strange wobble with stunning precision, perfectly matching the observed data. He knew he had done it. He had found the correct description of gravity. On November 25, 1915, he stood before the Prussian Academy and presented the final elegant field equations of general relativity. He had won the race, and more importantly, he had revealed a new and profound truth about the workings of the cosmos. Einstein's theory of general relativity was a mathematical masterpiece, and its success in explaining Mercury's orbit was a powerful piece of evidence. But for a theory so radical, it needed more. It needed a new, dramatic, and undeniable prediction that could be tested. Einstein had already provided 1 year earlier. If gravity is the curvature of spacetime, then the immense mass of the sun should bend the fabric of spacetime around it enough to deflect the path of starlight passing nearby. During a total solar eclipse, when the sun's brilliant disk is blocked by the moon, the stars near the sun should appear to be in slightly different positions than they normally are. The First World War delayed any attempt to test this prediction. But, after the war, the English astronomer Sir Arthur Eddington, a Quaker and a pacifist, saw an opportunity not only to test a revolutionary scientific idea, but also to help heal the wounds of the conflict. He championed an expedition to observe the solar eclipse of May 29, 1919. A collaboration between a British astronomer and a German scientist's theory was a powerful symbol of international cooperation. Eddington led one team to the island of Principe off the coast of Africa, while another team traveled to Sobral, Brazil. Their mission: to photograph the stars around the sun during the precious few minutes of totality. The expeditions were a tremendous challenge. On Principe, the day of the eclipse was cloudy and rainy. Just as the eclipse began, the clouds parted for a few brief moments, allowing Eddington to capture a handful of photographic plates. When the teams returned to England and carefully measured the positions of the stars on their plates, comparing them to photos of the same star field taken months earlier, the results were clear. The starlight had indeed been bent by the sun's gravity, and the amount of deflection matched the predictions of Einstein's general relativity almost perfectly. Newton's universe of straight lines and simple forces was gone. The announcement of the results in London created a global sensation. The headlines were dramatic: "Revolution in Science, New Theory of the Universe, Newtonian Ideas Overthrown." Overnight, Albert Einstein was transformed from a respected but obscure German physicist into a worldwide icon, the ultimate symbol of genius. His wild hair and gentle eyes became instantly recognizable. He was a celebrity on par with movie stars. The confirmation of general relativity was more than just a scientific victory. It was a moment of hope and wonder for a world weary of war, a testament to the power of human curiosity to reveal the deepest secrets of the cosmos. In the decades since Einstein's death in 1955, his theory of general relativity has moved from the realm of esoteric theory to a fundamental part of our modern technological world. One of its strangest predictions is that gravity affects the flow of time, a phenomenon known as gravitational time dilation. The theory states that time runs slower in stronger gravitational fields. This means a clock at sea level, closer to the center of Earth's mass, will tick ever so slightly slower than a clock on top of a mountain. This has been experimentally verified with incredibly precise atomic clocks, proving that your head is aging infinitesimally faster than your feet. This isn't just a curious fact. It's essential for a technology millions of us use every day, the Global Positioning System, or GPS. The GPS network relies on a constellation of satellites orbiting high above the Earth. These satellites carry atomic clocks that are crucial for pinpointing your location. Because the satellites are in a weaker gravitational field and are also moving at high speeds, their clocks run faster than clocks on the ground. Without correcting for both special and general relativistic effects, about 38 microseconds per day, the entire GPS system would fail. The errors would accumulate, and your GPS navigation would be off by about 6 miles every single day. Every time you use your phone for directions, you are relying on Einstein's genius. General relativity also predicted the existence of objects so dense that their gravity warps spacetime to an extreme, creating a region from which nothing, not even light, can escape. At first, Einstein himself was skeptical of these bizarre objects, which John Wheeler later named black holes. For decades, they remained a theoretical curiosity. Today, however, astronomers have found overwhelming evidence that black holes are real. We have observed stars orbiting supermassive black holes at the centers of galaxies, including our own Milky Way. We have even captured an image of a black hole shadow, a dark silhouette against the glowing gas swirling around it. Perhaps the most dramatic confirmation came in 2015, exactly 100 years after Einstein presented his theory. Physicists at the Laser Interferometer Gravitational Wave Observatory, or LIGO, announced the first-ever direct detection of gravitational waves. These are ripples in the fabric of space-time itself, created by cataclysmic cosmic events. The signal they detected was from the collision of two black holes over 1 billion light-years away. For a fraction of a second, this event released more energy than all the stars in the observable universe combined, sending a tremor through space-time that was finally detected on Earth. We can now to the universe, hearing the echoes of Einstein's curved space-time. Even after the triumph of general relativity, Einstein was not satisfied. He spent the last 30 years of his life, primarily at the Institute for Advanced Study in Princeton, New Jersey, chasing an even grander vision. He dreamed of a unified field theory, a single, all-encompassing theory that could describe all the forces of nature, gravity and electromagnetism, within one elegant set of equations. He believed that the universe, at its most fundamental level, was simple and elegant, and he searched tirelessly for the master equation that would reveal this ultimate unity. It was a quest that he pursued with relentless determination, but one that he would not live to complete. The challenge became even greater with the rise of a new and baffling theory of the very small quantum mechanics. This new physics described the strange, probabilistic world of atoms and particles, a realm governed by uncertainty and chance. Einstein was deeply troubled by it. God does not play dice, he famously quipped. His theory of general relativity was a classical theory, describing the smooth, predictable curvature of space-time on a grand scale. Quantum mechanics, on the other hand, was messy and statistical. The two great pillars of modern physics seemed fundamentally incompatible. How can the smooth fabric of space-time described by relativity coexist with the chaotic, quantized world of particles? This remains the single biggest problem in fundamental physics today. The search for a unified theory continues, now with the goal of uniting general relativity and quantum mechanics into a single framework, a theory of quantum gravity. Physicists around the world are exploring mind-bending ideas like string theory, which suggests that fundamental particles are tiny, vibrating strings of energy, and loop quantum gravity, which posits that space-time itself is made of discrete quantum chunks. These scientists are the intellectual heirs of Einstein, continuing the quest he began for a single theory that can explain everything, from the Big Bang to the fate of the universe. Albert Einstein's legacy is not just in the equations he left behind, but in the profound questions he taught us to ask. He showed us that the universe is not only stranger than we imagine, but stranger than we imagine. He taught us the power of curiosity, the importance of questioning authority, and the incredible potential of the human mind to grasp the cosmos. His journey from a curious boy with a compass to the architect of our modern understanding of gravity is a timeless story of imagination and persistence. And his unfinished symphony, the search for one ultimate theory, continues to inspire a new generation of explorers on their own voyages into the unknown.